Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Kern Schools Federal Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, and the Kern High School District, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon. I'm Marylou.
And I'm Cindy, and this is Do the Math, and you can get a hold of us at 636-437, or sorry, 4357. You can email us at dothemath@kern.org or watch us online at dothemathonline.net, and also look for us on social media.
Yep, Facebook, Twitter, all that wonderful stuff. Okay, so how's your afternoon going?
Pretty good.
Well, obviously we're not Mike, are we today?
Right.
All right, well, let's get started with our Math in the News today. Cindy, what color of eyes do you think is the most rarest?
The rarest. Green?
Green? Okay, so let's look at this study. You might just belong to one of the world's most exclusive groups without realizing it if you have blue eyes. You've got one of the most rarest genes. There's 17% of the world's population has blue eyes. In contrast, more than 50% of the global population is believed to have brown eyes. Obviously, you and I both have brown eyes. Now, my husband's side of the family, they're all blue eyes. While blue eyes may be rare, they're among the most common eye colors at birth. However, just because you're born with blue eyes doesn't necessarily mean that you will keep that. They will eventually change over to either the brown or the hazel colors or green. A study found from between the years of 1905 to 1951, there was a number of change from blue eyes. It dropped by 25%. Now you might think, why are we talking about eyes and how does this have to do with math? Okay, why? Because we're talking about the drop, how it's becoming more rare to have blue eyes. So let's talk about the definition of percent of change. So to find the percent of change, if we wanted to find out that, figure out the 25%, what we're going to do is here, we have our percent of change, which is the amount of change divided by the original amount. So the amount of change, that, what do you think that means?
So how much it changed by, so you have to subtract.
Exactly. So we would subtract the 1951 from the 1905 to find the amount of change, and then we're going to divide it by the original amount, being the original
The one that happened first.
Exactly, 1905, to find that out. So let's look at an example. So let's use money. We have some money here. Say we want to find the percent of change from $300 to $250. We're going to take that difference, and then we are going to divide it by $250, which being the $250 being the original amount. So we know the difference is $50, and we're going to divide that by $250. And we find that our solution is 1/5, which equals approximately 2/10 or 20/100, hence giving us our 20%. Now, do you know but what the most rarest is? Red hair and blue eyes.
Red hair and blue eyes, yeah.
Red hair and blue eyes is the most rarest, and that is our Math in the News today. And And we obviously have a special guest today. Why don't you let everybody know your name and where you come from?
Hi, my name is Tilak Leva. I am in the 6th grade.
At what school, Tilak?
I go to Ronald Reagan Elementary.
And Tilak, have you been there since kindergarten?
No, I've only been there since 3rd grade.
3rd grade. What is your favorite thing to do at Ronald Reagan?
Math.
Math? All right.
Good
now,
answer.
are you part of any math competition or any math groups there on campus?
Yeah, I'm trying out for math counts.
Oh, good luck. Is that a lot? Are there a lot of students who try out for math counts?
Like, there's 10 people trying out right now because a few of them stopped from the beginning because they thought it was getting a bit too hard.
Oh, okay. But you're hanging with it, right?
Mm-hmm.
Well, good luck to you on that. And you brought some problems with us, correct?
Yes.
Okay. Why don't you go ahead and head over to the board, and I will read this off. It looks like you're working on square roots, correct?
Yep.
Okay. Go ahead and over to the board. Let's try this problem. Let's start with this. We have
Doesn't matter which one.
open parentheses. Do an open parentheses. And -2, close parentheses, and you have an exponent of 2. Can you kind of explain how to solve that?
Like, so since it's squared, it would have to be -2 times -2, giving you an answer of +4.
Yes?
Yeah. So this would equal 4.
Okay, I'm going to give you one more. Try this one. And maybe Cindy can help you out if you're struggling on it. We have a open parentheses, negative, and we have the square root of 3, close parentheses, squared. Can you walk us through that?
This would be -√3 times -√3, which equals, since the square root of 3 equals the square root of 3, so if the first square root of 3 has to equal a number times itself would give you 3. These two would equal 3, and then the negative sign, so negative times negative is a positive, so it would be +3. So your answer is 3.
Okay, so I think some people, you did it great. I just know some people might get confused about how you knew that, that times that equal just 3 by itself.
Mm-hmm.
Is there, you kind of explained it a little bit, but how did you know it just came out as 3?
So like, for example, if it was like square root of 4, like the answer would be 2, because 2 times 2 equals 4.
Okay.
Like for 3, like we do not have an exact number yet, but we're saying if that number, which the square root of 3 would equal, times itself again from here, would equal 3, and then the two negatives would cancel, making it a positive.
Yeah. And so another way just also to look at it is you can go, since 3 times 3 is 9, the square root of 9 would give you the 3 also. So that's another way of looking at it. But yeah, I see what you're saying. Whatever that number is going to times by itself anyway, so it's going to get back to 3. Okay, good job.
Great job. Come on back here.
You just stick it right there.
Well, we got a lot more going on, but now we are going to go to our live shot today with Devin, and Devin is at the Southern California Orthopedic Institute. To you, Devin.
Hey, thanks a lot, Marylou. Hey, despite looks, this is the best health I've ever been in a doctor's office. We're here live at SCOI, the Southern California Orthopedic Institute. Now, when you hear a lot about doctors, you think very general, but there are a lot of specialties, doctors that specialize or focus on one part of getting better. And that's what we're going to talk about today is one of the specialists with the Southern California Orthopedic Institute. Today we're going to talk with Dr. Karl Ball. Dr. Karl Ball, thank you for joining us today on the show.
Hi there. Good to
So,
see you.
Doctor, tell us a little bit about your specialty here with Scully.
Sure. So I'm a hip and knee specialist. So I basically deal with anything involving the hip and knee. Most of my patients tend to be arthritis patients. So I see a lot of people who have really bad hip or knee arthritis. And what that basically is the joint that helps your hip or knee move around. When the cartilage gets worn out over time, the bones get closer and closer together. They start to grind together, and that can cause pain and be disruptive to the ability to walk and do normal daily activities, that kind of thing.
Now, a lot of our viewers normally think of cartilage, and they might be familiar with it as being the soft tissue in their nose or their ears. They don't generally think of cartilage as being in the hip or the knee. So what role does cartilage play in those joints?
Sure. So cartilage actually is an incredibly smooth surface. It's highly viscous. It's something that you can think of it, it's even smoother than ice. Things glide really smoothly on ice. Cartilage is even better than that. Nature does a great job. So when a joint, your knee or hip joint, moves around easily without pain, the way it's able to do that is it has this really smooth surface that it can kind of easily glide without a lot of pain or effort. The problem is that cartilage, if its cartilage gets damaged, it can't really heal itself. So if you can't heal the cartilage, over time it starts to wear up, accumulate damage over time. That's why when you see older people and they say, oh, my arthritis, my cartilage, it's because they've had a lifetime of accumulating small injuries and just wear and tear on their cartilage. I like to use the analogy, it's like tread on your tires. Eventually you drive your car long enough, your tires are going to wear out. Some people drive really aggressively and can wear it out really fast, and then other people, it takes them a long time to wear it out.
And there's a misconception about arthritis that it is exclusively in the domain of the older population, but you see a lot in sports medicine as well that arthritis is a common malady that might face a lot of younger athletes.
Yeah, absolutely. We do definitely see a lot of athletes here. We see, high school and younger kids all the way up to, 100-year-old patients. And I actually, because there's some things where there's something called a hip dysplasia, where the hips can actually be born where they're missing either parts of the bone that they're supposed to have, or it has an unusual shape to it. And I've actually done hip replacements for patients that were 28 years old, where basically they had a hip that looked like an 80 or 90-year-old's hip, even though they're only, almost 30 years old.
Now, you say hip replacement, and that sounds like a large endeavor, because when we generally think of the hip, that's one of the largest bones of the body. So when we talk about hip replacement, are we talking about the entire bone itself, or what does that process look like?
Yeah, sure. So hip replacement, I have a model right here I can kind of show that shows a little bit about what it is. So here's an x-ray of a patient who has arthritis, and on their left hip here, you can see that the bones are actually touching each other. So
that shouldn't happen.
That shouldn't happen. You're correct. That's the bone-on-bone arthritis you hear everybody talking about. And if you look at the other side, you'll notice there's a nice gap between the bones. That's what you want to see. So gaps are good, no gaps are bad. So this patient has really bad arthritis. Now, this model here shows what we do for that. So basically, in the operating room, we take the patient back, cut the neck of the femur right there with the saw. This is like power tool, carpentry kind of stuff.
Very powerful.
And you cut the bone like this, and then you actually clear out a space inside the femur right there.
So you're hollowing out the inside of that heavy, large leg bone.
And the bones, the way bones work is actually the outer surface of the bone is dense, really hard bone, while the inner portion of the bone is this spongy, soft bone. So you clear out some of that soft bone. We have a metal implant with a ceramic head that looks like this, and we wedge that in there until it's real solid. So we get that in there. The cup or acetabular side, we clear that out using a tool that looks like a cheese grater on a spinner. We basically clear that out, impact a metal cup with a plastic liner, and then we put the whole thing back together again, and it allows the hip to move around without grinding the bones anymore. So that's what a hip replacement essentially is. So you cut it right there, you clear out the surface right there, and then you replace the grinding bone parts, and then the patient can wake up, they can walk the same day as surgery. I have some patients that even go home from the hospital the same day I do the operation.
That's remarkable. And so you're able to basically replace the grinding parts together with two smoother surfaces, the one on the leg piece and then the one inside the hip joint too.
Yeah, absolutely.
so things move a little bit more smoothly. And later on in the program, we're going to talk a little bit about how math applies tremendously, not just in the general field of medicine, but with these types of procedures in particular. So 6th, 7th, 8th grade, you're dealing with ratio, proportions. 4th and 5th grade with measurement. A lot of what you're doing is exactly what Dr. Balch does every day when planning these types of procedures. So later on in the program, we're going to have a conversation, actually look at what that piece of the math puzzle looks like in regards to the work here at the Southern California Orthopedic Institute. But for now, we're going to send it right back to the studio. Marylou, take it away.
Thanks, Devin, and we will hear more from you from the Southern California Orthopedic Institute in just a little bit. We have Tilak with us in the studio, but we're going to come back to you with some more problems that you have. But first, we have a caller in studio. Hello, Caitlin. How are you doing today?
Good. How are you?
Great. And what school are you calling? Do you go to?
Ronald Reagan.
Ronald Reagan. Okay. Can you tell us what your problem is?
80% of the 6th graders at Harrison Middle School are going on a field trip to the museum. There are 685 students in 6th grade. How many students are going on the field trip?
Okay, so 80% of the students in 6th grade are going, correct?
Yes.
And there are 685 students in 6th grade.
Yes.
Okay, so you basically need to figure out how many out of all those students are going to go on the field trip.
Yes.
Okay. So how did you start it?
So,
Or how do you know how to start it, I should say? Okay, go ahead, sorry.
80% equals 80 over 100.
Okay.
And that can be simplified into 8 over 10.
Okay.
And then I did 8 over 10 times 685.
Okay.
Then I cross-canceled, where I simplified the 8 into a 4 and the 10 into a 5.
Oh, so you simplified the 8/10 down even more?
Yes.
Okay. So
And then-
4/5 times 685?
Yes.
Okay.
And then I simplified even more, and I divided 10 by 5 and 685 by 5.
Okay, hold on. So you lost me a little bit. Okay, so you said you started with 80 hundredths.
I mean, I divided 5 by 5.
Oh, there you go, because you got back to 10. I was like, wait, you went back to 10 again. Okay, so you cross-canceled basically, and you divided them both by 5, yeah?
Yeah.
Diagonally. So you got 1 on the bottom for the 4/5 became 4 over 1. And then what'd you get when you divided 685 by 5?
137.
Okay.
I mean, not one. Yeah.
Is that what you got?
Yeah.
I'm trusting you here. So you have 4 over 1 times 137 over 1. So really you just end up with 4 times 137.
Yeah.
Okay. And did you go ahead and multiply that out?
Yes.
What did you get?
548.
548. So 548 students are going on the field trip?
Yeah.
Okay. And then we could kind of just make sure that seems reasonable. So 80% is above half, right? 685, half of that, about 340, a little bit more than 340. So 548 is above that amount, but below 685. So that's a reasonable, we can kind of just estimate that it's a reasonable answer, correct?
Yeah.
Okay. So that's definitely one way to solve it. Thank you.
There you go. And thank you, Caitlin. You just won yourself Chick-fil-A. There you go, and thank you for your call today. So, Tilak, you ready to work?
Yes.
Okay, head on to the board, kiddo. All right, just a quick reminder that
so
we
hold on, let me
do
remember how
have tutors here till 5:30 tonight. Give us a call at 636-4357, or if you're calling from San Luis Obispo, you can call us toll free at 1-866-636-6284. All right, Tilak, you ready?
Yep.
Okay, here we go. So, the problem is 3x squared minus 9x plus 2. Oh, that's a plus. Oh, there you go. Yep, plus 2 equals 0. So you're going to solve the equation by applying the quadratic formula.
So the quadratic formula is ax squared plus bx plus, oh God,
Just try not to touch it, that's all. Yeah, you
Plus
can.
c equals 0, and then in that you have to solve for x, so x would equal negative b plus minus the square root of b squared minus 4ac over 2a. So using that, we could know that the a, we fill the a in for the 3, the negative 9 for the b, and the c is the 2. So if it's negative 9 and it's supposed to be negative, you can make it a positive 9 plus minus the square root of b squared. So negative 9 squared is 81 minus a times c, which is 6 times 4 is 24 over 2a, and a is 3, so we'll make it 6. So then 8 plus 24, no, minus 24 equals 57. And since there's no square root
Here,
for
hang on just a
57,
second. Let me move this for you a little bit so that you, wait. Yeah, there we go. So you have a little more room.
so since there's no square root for 57, your answer would be x equals 9 plus root 57 over 6. So there's your answer.
Wow, great job. Okay, so are you ready for one more?
Yep.
Okay, so this is another quadratic formula. 3x equals, oh no, just 3x.
I'll just erase it with the, well, what did I do?
Oh, here.
Okay,
Okay,
I got
there
the
you
match.
go.
Okay, 3x equals.
Equals 3x squared minus 6.
So using the same formula, you want the question to equal 0. So we move this over by subtracting 3x on both sides. So when you do that, this would be 0 equals 3x squared minus 3x minus 6. I didn't subtract anything with the 3x because this is an x squared and you cannot subtract an x squared from an x. Then I started using the formula. That was x equals negative b plus minus square root of b squared minus 4ac over 2a. And that would be 3 plus minus b squared, which is 9, plus, because this is a negative 6, so a negative times a positive is negative 18 times a negative 4, which would make it positive, and 18 times 4 is, carry the 3 and you get 72. So 72 over 2a, and that would be 6.
Here, I'll move it for you a little bit.
Then that would be 3 plus minus 81. 81 over 6. 81 has a square root because 9 times 9 would give you 81. So that would equal 3 plus minus 9 over 6. Since we have a number here, we could use the plus and minus. So if it was a plus, so 3 plus 9 is 12 over 6, you would get 12.
Here, I'll
So
move
x
that down for you.
equals 2, and then if it was a minus, it would be negative 6 over 6. 6 would cancel, leaving a negative 1. So that's your answer.
There you go. Nicely done, Tilak. Come on back over here, kiddo, okay? I think I could have used you to help me with my math homework when I was maybe in high school. Nicely done. Okay, again, remember, if you need help with your homework, we have tutors here until 5:30. You can call us at 636-4357, or if you're calling from San Luis Obispo, you can call toll-free at 1-866-636-6284, and we'll be right back in just a little bit.
Today we're at Richgrove Elementary School, home of the Warriors, and we're here to
Do the math!
All right, we're back at Richgrove Elementary School, and the kids had some blocks. They've got some cubes that they can connect together. Had a little bit of time to experiment with them, see what they wanted to build on their own. Now we're going to see if they can build a specific item or put together the blocks in a certain way according to the cards. So, are you guys ready? All right, here we go. So each of you, the pair of you, is going to get a separate stack of cards to do, all right? And just randomly pass those out. So there are 4 different things. So your task is completely different than anybody else's task, all right? So if you look at somebody and go, oh, theirs looks like that, it will look a lot different than yours because they're all completely different. So take the cards apart, spread them out, and take a look at all of the clues and see if you can build exactly what we want based on those cards, all right? So if you need to trade blocks with somebody else, because some are color specific, all right? So take a look at the cards, look at them all together so that you have an idea of all of the different things you need to do, all right? Go to work, build it.
Can we use one red and 2 blues? Can we use one red and 2 blues? And 2 yellows. But 2 blue blocks do not touch each other. So the blue is between and then the yellow is above the blue and black. So also we need it.
You guys think you're all through? Let's take a look. The 2 red blocks do not touch each other. All right, that's fine. Each red block shares an edge with the yellow block. Now, an edge is going to be different than a face, okay? So let's take a look at these. So this right here is a face. This right here is an edge, all right? So if they were like that, the edges meet. If we do it like that, the faces meet. Does that make sense? Okay, so keep trying. And it may not be just one level. Think of that. It might go up a little bit. All right, so keep working on that. But you had a couple of them were correct. You finished? Yep. Let's take a look. You guys are pretty hot shots here, huh? Let's take a look. All right. There are 2 yellows,
2 yellows,
2 blues,
2 blues.
1 green, 1 red. That one's set. There are 6 blocks in all in a tower 6 blocks high. The yellow block is on top.
It is?
Each of the blue blocks shares a face with the green block.
The face is in the bottom.
Right. The red block is above the green block.
It never said it close to it.
Right, it never said it had to touch it as long as it's above it, right? So good. No 2 blocks of the same color touch each other.
It's not touching.
Right, and they're not touching either, are they? Right, so let's take a look at the last one. One of the yellow blocks is above the green block. The other block, the other yellow one, is below it. Nicely done. You girls have solved it. Good work. All right, now here's what I need you to do. What I want you to do is I want you to come over and see if you can help with this group right here, all right? Because I think you guys are getting a little closer on track, right? So go over, see if all of those clues, now remember, faces and edges, right? You girls know the difference between a face and an edge? There we go.
Blue. And yellow?
One yellow? One yellow?
So it is showing an edge, but it never said the face.
Blue shares a face with yellow, correct? There is a red block on the bottom level, and there is. Nicely done. All right. All right. Do you guys have fun doing that? Yeah. All right. So being able to read those directions and see if you could build exactly what they were looking for, specifically to the task at hand, and that's what the students were doing in 4th, 5th, and 6th grade at Richgrove Elementary.
And welcome back. We have a special guest in audience in studio today, and it is Tilak. And again, Tilak, what school do you go to?
Ronald Reagan Elementary.
Okay, you were talking about math counts. Are you excited about Math Field Day at all this year?
I don't know what that is, but
Oh, well,
it's
you're
math stuff.
It's
but
math stuff,
okay.
and you're going to have to find out about it because it's a whole lot of fun. But for now, we're going to go back to Devin at the Southern California Orthopedic Institute.
I'll give my thumb, please. Hey, thanks everybody. Welcome back. Thank you very much, Marylou. We're back here at the Southern California Orthopedic Institute. Boy, you should have come to us maybe 30 seconds sooner because this part, well, you know what, I've done enough damage here, but let's just say these are, safe displays. These are not toys, ladies and gentlemen. Please be gentle with the displays whenever you visit a medical facility back here at Southern California Orthopedic Institute. And before our last break, we were talking a little bit about hip replacement and some of the planning that goes behind it. And we're back here with Dr. Karl Ball. First of all, I apologize for playing around with the goods. I'm sure you're insured for it. But we're talking a little bit about some of the planning and the math that goes behind a hip replacement surgery. And what you have here is kind of a model using some of the tools that you use to plan before the surgery takes place. And so we were talking a little bit about this patient, which is the same one we were looking at in the other room here.
Yeah, sure. So we basically have the same x-ray that you saw in the clinic room there. And then we've tried everything else, nothing's worked, and now we're going to do a hip replacement surgery for the patient. So I import the patient's x-rays into this trauma CAD system. So this is a kind of design system. And what we do is first we have to calibrate the image. So to do that, we have this calibration sphere, which is on the x-ray there. So we have a little ball down there, and we know the size of that sphere. So that is a preset size. So with the computer, I can calibrate it based off of that sphere to say, hey, this is what the dimensions are.
So on an x-ray, this kind of serves as like the map scale. So if you know this is a certain size, then you can use a ratio or a portion to determine what the other distances are elsewhere on the image.
Yeah, absolutely. So, and for me, I really want to make precise calculations to plan the surgery before I do it. And to be able to make those precise calculations, you've got to know what the lengths are. You've got to be able to know what the proportions and ratios are of everything you're looking at. Based on how the patient's standing, how far away the x-ray machine is from them, all of those things can affect the size of the bones on the x-ray. And so if you don't have something to gauge what a distance is, you'll never know what you're looking at. And even with the same patient, if they stood a little closer this time, a little further back, everything's going to be different measurements, everything's going to be different if you don't have calibration.
So when that x-ray tech tells you, hey, you have to stand a certain way so we can take that x-ray, no matter how old you are, it matters just for that reason.
Yeah, absolutely. So we set the calibration, then we know our sizes. What I do is I draw a line that goes across the bottom portions of the pelvis or the pubis bones here, and I make lines that go to the same point on each hip. So I say, okay, that's about the center point of the lesser trochanter, or this bump of bone here, and then I make a line to the center point of this bump of bone on this hip, and it calculates out for me here that this left leg where we're going to do the hip replacement is 5 millimeters shorter than the right side. So I know before surgery that this patient's hip is already 5 millimeters short.
And that comes from the grinding away of the cartilage.
Yeah, so as that cartilage wears away and the joint loses that space, you lose about 5 millimeters of cartilage. Now this hip is shorter. So if you really want that hip replacement to recover fast, you want it to feel natural, you want to restore all of that length that got kind of taken away. So the next part of my planning here is I actually superimpose a copy of what the cup that I put in looks like. And I'll do this quickly for you guys here. So you put that in there where that's going to be, and that helps me figure out what size. I need a 56 millimeter cup, and that helps me plan that. And then that stem that goes into the femur that you saw earlier, I plan, okay, I'm going to cut my femoral neck right there. I want about a 36 millimeter head size, and let's do a size 6 stem. And I can plan out what I want to put in there. And this is about where that's going to go. And now that we've put this in here, I can kind of calculate out this is going to lengthen the leg 5 millimeters and increase the width of the hip about 1 millimeter if I put that part in. So now, okay, we know we were 5 millimeters short. Now we've restored that leg length and we've equalized the patient's hips. So this lets me go into the operating room with a plan before I have to go in and execute the surgery. So that way I already know what size parts I want to do, where I want to put them, what I need to do to make this kind of all work.
Now, one other feature of this that I'm noticing is this idea of offset, and you can see with these lines as they intersect, they create an angle, and so the angle of that offset is going to be really important because you don't want that hip to be replaced and all of a sudden the leg is at a different angle than it was before.
Absolutely, that affects how natural it feels. If you widen the hip significantly, it over tightens the muscles and gets uncomfortable. If you lose a lot of offset, if the muscles get really loose and floppy, they can't pull very hard. So the people get weak. So if you don't have good, if you don't properly restore the width of the hip, you either lose, you lose strength, or it becomes too tight and painful. So hitting that sweet spot, hitting that perfect spot really makes the most natural hip and makes you recover the fastest.
With the offset, we're looking at around 130 degrees of an angle right there. So a little, it's more than a right angle, but not quite a straight line, somewhere kind of right in the middle between those.
Yeah, and we have, from all the research and studies that the doctors have done looking at this stuff, we know what the optimal position to put things in is. We know, okay, I want this to be 40 degrees, I want this to be 15 degrees. We have kind of a preferred spot where we know that patients will do really well.
So when we come back, we're going to take a look at some of the statistics generated here at the Southern California Orthopedic Institute in regards to the work being done here and the field as a total. But for now, we're going to send it right back to the studio. Marylou, take it away.
Thanks, Devin. Tilak, have you ever had x-rays done?
Yes.
Yes. Do you understand why you have to be so in a certain position and you can't move?
Yeah.
What about you, Cindy?
Yes.
Yes. All right. Okay, so you ready to do some more work?
Yep.
Okay, back to the board, kiddo. Okay, here we go. Now, yesterday, Tilak, we talked about prime factorization, okay? Can you quickly tell us the difference between prime factorization and factorization with the quadratic formula?
So I'm going to do prime factorization here. So like if it was the prime factorization of 20, you'd break it up into two numbers such as 4 and 5, because 4 times 5 would give you 20. But then 4 is not a prime number. 5 is, so 5 will stay. but then 4, you could break it down into 2 and another 2, and both of those are prime numbers. So the prime factors of 20 would be 2, 2, and 5. While factorization would be like 6x squared plus 13x
plus
6 would
equals 0.
Equals 0 would be like, technically you could cross multiply like this, and like in this method you gotta do a lot of testing. So like 1 and 6, so we could see if 1 and 6 works, then 6 and 1. 6 times 6 is 36, so that obviously wouldn't work already.
So how do you know it doesn't work for someone that's not sure, what you mean by it doesn't work? What's it supposed to equal?
So technically it's supposed to equal this middle value, which is 13. So 6 times 6 is 36 plus 1, because 1 times 1 is 1. That gives you 37, and you're way over 13.
I see. So what you're doing is you're multiplying the diagonal, and then you're adding the two things together?
Yep.
Okay.
Then after that, and then you could try 2 and 3 for both of them, because 2 times 3 equals that. So 2 and 3. And here's something else. You also don't have to like put it all in the order from like 2, 3, 2, 3. You could like mess around with it and like make the bigger number on the top. So like 2, 3, 2, 3 wouldn't work, because 3 times 2 is 6 plus 2 times 3, which is another 6, which equals 12. So you're 1 under, so that wouldn't work. But then if you did it with 3 on the top and then 2 on the bottom, 3 times 3 is 9, and then 2 times 2 is 4. So 9 plus 4 is 13. And since 13 equals 13, you write it in this order, but then since there's no negative sign here, it's going to be a plus. But this has to be an x, because then they have to have the x for the middle value. Then when these two multiplied have to equal 6x squared. So one of them has to be an x and the other one has to be an x too. So your answer would be 2x plus 3, and then 3x plus 2.
Let me go ahead and move this down for you a little bit so you have more rooms in there. There you go.
So then the difference is that here you're listing the prime factors, while here you're like almost like
You're
solving
just like
it.
making it a multiplication problem before you solve it, right?
Yeah.
Because it still says equals 0, so you haven't finished it all the way yet, right?
Yeah. And then like technically you want to make one of these 0, because when they're multiplied they'll equal 0. So if you wanted to make this 0, it's going to have to be x equals negative 3 over 2, because if it's negative 3 over 2 times 2, the 2's would cross and it would be negative 3 plus 3, which equals 0. So negative 3 over 2. And then if it's 3x plus 2, we could do 3 times negative 2 over 3, letting that cross cancel, and it would be negative 2 plus negative 2, which equals 0. So it could also be negative 2 over 3. So that would be the answer there.
Wow. Well, you know what, Tilak, for that, because you've done such an amazing job today, we're going to give you a Chick-fil-A, free dinner for Chick-fil-A, okay? Congratulations. Hey, we've been talking about the quadratic formula quite a lot today, but we're going to throw something else at you that you don't quite know yet, but you will get there. So Cindy, let's show him some scientific notation.
Okay.
Let's start with the number 2,103,000 thousand.
Just, okay, well, I
Yep,
was making
that's
sure
it.
you were going to
Yeah,
say.
nope, that's it. Let's go ahead and show him how to turn that standard form to scientific
Okay,
notation.
so just so you kind of get why the scientific notation is around. So it's to show, it's a simpler way to write really large numbers or really small numbers without having to write like all the zeros out. Have you ever had your calculator, the answer's too big to fit on the screen and it gives you like a little exponent on there? Have you ever seen that happen? Like scientific calculators will put numbers that won't fit, they'll put them in scientific notation. So if you're familiar with it, then you'll know what that means when you see that on your calculator. Yeah, it does use an E in it on the calculator, you're right. Okay, so scientific notation always looks like it has some number that's not 0, so 1 through 9, and then a decimal. And it doesn't matter what's back here. It can be a lot of numbers or just a few. It depends on the problem itself. But then it's always got a power of 10, so 10 to some power. So some number here that's not 0, and then a power of 10. And that power of 10, what happens when you multiply by 10? What happens to the decimal?
Decimal moves to the right.
Yeah, so the power of 10 is just about moving a decimal, right? So scientific notation, if we want to take this number and make it look like this, we need to get the decimal so that there's only one digit. So we basically need, right now, the decimal's there, but we need to put it so that there's only going to be one number on the left of it. So we need to put it right here, okay? So we rewrite this with the decimal where we want it, and we have to write everything number-wise, that's not 0. We can drop the zeros that are at the back, but not in the middle, okay? So then we're going to put, multiplication. We have to figure out what the power of 10 is, okay? So since our decimal's moving, it's basically how many times did we move it?
3. So it would be 1, 2, 3, 4, 5, 6.
Okay, and since we moved it left, it's kind of like dividing. So what happens is when we move it left, wait, no, I'm thinking backwards. This is this. Okay, because if we wanted to turn this number into a regular number, we would have to move it right to get 6.
But then to get from here to there, you'd have to divide by 10.
Yeah, technically we're dividing by 10s to get here, but this is the correct scientific notation. So can I add my own problem in?
Let's go ahead and give him a decimal so he sees it the other way.
Yeah, let me show you one where the power is negative because I accidentally said it backwards on that one. So 0 point, I don't know, let's just make up one. Let's say you started with a really small number. Instead of a large number, we start with a small number. Okay. So if we started with this number, we want to make it look like that. We want to get the decimal to the correct place so that we have one digit that's not 0 and then the decimal point. So you can grab the pen if you want to give it a try.
1, 2, 3, 4, 5, 6, 7.
Okay, so we want to get it right here? Okay. So then let me move this down for you so you have a little bit of room. Ready? Okay, so go ahead.
Okay, and then that's going to be 2.51. And since we moved it 1, 2, 3, 4, 5, no, 1, 2, 3, 4, 5, 6, 7 times,
yeah. 1, 2, 3,
would be multiplied by 10 to the 7.
Yeah, this is the case where you put negative to represent that that's a small number that, because if we were going to multiply it by regular 10 to the 7th, it would go to the right. But because it's like, how would you get this number back to normal is how you determine the sign. So to get this number back to what it's supposed to be, you would have to divide by a bunch of, to get it backwards. Or you have to move it to the left, and on a number line, negatives are on the left, so you could think of it like that too.
Okay, let's give him one more, see if he could do this on his own. Let's do the whole number, okay? Give him one more with a whole number.
Okay.
And Tilak, let's see if you could do this
So by
one
whole
on your
number, you
own.
mean
just any
the
number.
larger, you have the larger
Yep.
number? Okay. So let's do, I don't know, let's make it.
Okay, Tilak, see if you could solve that one on your own.
Okay.
What would you do first?
So I would move the decimal there, and then it would be 5.21, and I don't need all the zeros. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would be times 10 to the power of 10.
And that's it. Okay, now Cindy, I have one for you, and you have about a minute and a half. You ready?
Yep.
54 and 6800ths times 10 to the 6th. Real quickly explain why that's not scientific notation.
Okay, so it's not scientific notation because scientific notation always has to have one digit before the decimal that's not 0, and since we have a 2-digit number right here, we always need a 1-digit number, which means it's not in the correct spot, and we have to get it so that it would be after the 5 on the right-hand side of the 5. So we need to move it from here 1 space, okay, so that we can get 5 and 468 thousandths. And then since we moved it, but we already had a 6 here, what's going to happen is our power is going to change by 1, but where people they get confused is they're not sure what to do. They don't know if they should add 1 or subtract 1. So since we moved it from the right-hand side, it was a bigger number. Like if you picture this, if you turn this into a regular number, you'd have to move it to the right 6 times and then move it back 7 times to get right here. Our power increases by 1 since we moved it left 1.
And
We need
there
one
you
more
go.
10 to multiply.
There you
by.
go. And you know what? Come on over here. You have something new to go back and share with all your classmates, huh? And say, here, try this. Or you could teach them, right?
Yeah.
You're ready for 8th grade, aren't you?
Maybe.
Because that's an
maybe.
8th grade
Okay. All right. Well, we are going to head back to Devin at the Southern California Institute, Orthopedic Institute.
Well, thank you very much, Marylou. Back here at Southern California Orthopedic Institute, wrapping things up on a wonderful Wednesday here at Dr. Karl Ball. And, we were looking at a lot of the x-rays today of our patient here. A lot of those are the befores. Let's take a look at the after and see what resulted from all this planning and work that went into this, gentleman.
Yeah, so you plan the operation, you go into the surgery with a plan. Here's the same patient. So using the calculations we did, we've been able to equalize the patient's leg length. So you can see that bump of bone, the lesser trochanter, it's at the same point now when you draw that line. So now we've equalized the leg lengths. The width of the hip has been equalized within a millimeter. So this is something that's going to feel natural to the patient. They're going to recover quickly. This patient, within 2 weeks, no cane, no pain medications, driving, all that kind of stuff, even after a major operation. And he just loved it. So that's something where, doing the complex planning beforehand helps to shorten the length of the surgery, make them recover faster, all of that.
Put that right on the wall of pain-free frame. And, we mentioned how the industry has changed so much as far as just the last 20, 25 years, from going from just, okay, does my leg feel a little less pain, but I can move it a little bit more, to I want to be able to do everything I could have done 50 years ago with this new hip. And you track a lot of information as far as whether or not that's actually been the case after recovery.
Yeah, sure. So I like to keep pretty comprehensive data on my patients both before and after surgery. That helps me both provide data to my patients. I can tell them, hey, at 2 weeks, this is how much I would expect you to be hurting. This is how long you got to use a walker or a cane after operation. I can quote them, more specific data, so that helps them. So I have lots of data. This is knee replacement data that I've done, and I look at what was their range of motion before surgery. What was their pain? A scale of 1 to 10. What do you call your pain before surgery? Where's that pain at 2 weeks after surgery? Are you using a cane or a walker? Are you using pain medications? How much pain medication? And compiling all that data, I'm able to get averages and standard deviations from that data as well.
So you're talking about standard deviation. For our viewers around 6th through 8th grade, explain what standard deviation means.
Yeah, sure. So hopefully in class or somewhere you guys have seen that bell curve, right? And so the standard deviation tells you, you expect most people, the average patient, should be right down the middle of that curve, and then within a certain degree to either side of that kind of curve where the average is normal variation that you expect to see in a patient. Every patient's not going to be exactly the same, but you know what the average amount of variability tends to be. That helps us to identify what we call outliers, okay? And outliers are really important, the good outliers and the bad outliers. Good outliers may be somebody who just, wow, that patient recovered so much faster and did so great. What did we do with that patient that helped them recover so well? Can I do that for all the patients so everybody can recover better? Or you see a patient who didn't recover as well, and they're a bad outlier. You say, well, what went wrong with that patient? What could we do differently next time to prevent that from happening, or what could be learned from that? So being able to look at averages and standard deviations really helps me identify, where most of my patients should be expected to be, who are the high performers, who are the low performers, that kind of thing. And lets me do, statistics or other things that I want to do as well to kind of understand the data better.
So, it's an industry that's booming. There's always growth, especially in medicine and healthcare. There is no shortage. There's no job replacement really taking place. If one of our viewers is interested in getting into the field of orthopedic surgery and medicine, what would your recommendations be? As far as we're in 6th or 8th grade, where would you start? What would you pursue?
Yeah, sure. So, the road to becoming a surgeon is a very long road. So it's one that involves a lot of school and a lot of training. But right now, it would be important for you to set your foundation in the math and sciences, certainly. So things like math and statistics are very important to be able to understand research and science in general. Physics and biology are also extremely important to be able to understand, some of the things about, how the mechanics of things work, how do cells and the human body work. That's really laying the foundation for your studies that you would have in college, medical school, residency, fellowship, whatever, all the years beyond. So this is really the time to set kind of that foundation.
Well, Dr. Ball, it's a wonderful visit, a lot of insight onto something I think a lot of us just kind of take for granted sometimes, or only just kind of hear about. And we appreciate you opening up the Institute for us to come by and visit and to show our appreciation, as we do anytime we visit a local business. We want to thank you with the celebratory and commemorative Do the Math tile.
Awesome, thank you.
Dr. Balch, thank you so much for your time today and allowing us to stop by and kind of peek behind the curtain of the Southern California Orthopedic Institute. Right now, we're going to send it back to the studio. Marylou, last time today, take it away.
Thank you, Devin, and thank you to everybody out there at the Southern California Orthopedic Institute for allowing us to come out there today. Well, Tilak, you having fun today?
Yes.
Okay, so we have some presents for you. First of all, you won your Chick-fil-A. Yes, and now you are getting a wonderful shirt to go back and wear at school to show everybody about Do the Math. And you are going to be an ambassador. Do you know what that means?
No.
No, that means you are going to be a champion for our show. You're going to let everybody know, hey, call Do the Math. They're going to help you out, okay?
Okay.
All right. Okay, so they were talking about outliers before, earlier with the orthopedic. You were talking earlier that you guys do the mean, median, and mode in class. And I had asked you, do you also do outliers? And you said no, but next year you'll learn about those outliers. When they're talking about outliers, it's talking about something that is outside of the range. So say you have numbers 1, 5, 7, 99. What do you think the outlier would be?
99.
Exactly. Well, Tilak, it's been a pleasure having you here today. Thank you very much. Now remember that we have tutors here until 5:30 tonight. You can call at 636-4357, and that's it from us today at Do the Math. We'll see you next week.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Kern Schools Federal Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, and the Kern High School District, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.